Hello and welcome everyone to today's conference session, Smart Machining with On-Machine Metrology Feedback for Shop Floors. I'm Michelle Jacobson, the Assistant Editor of GIE Media Manufacturing Group of Publications. Today's medical developments, today's motor vehicles, today's e-mobility, and aerospace manufacturing and design. I'm excited to introduce our speaker today, Ray Karadayi. Ray is the founder and CEO of Applied Automation Technologies, Inc. He holds a Bachelor of Science and Master degree in Mechanical Engineering, specializing in automatic controls and robotics. He started AAT in 1987 as a Michigan, USA-based technology software company for the purpose of developing CAD-based software packages for quality control, adaptive manufacturing, and smart machining. He has more than 35 years of experience in software development in CAD-based measurement software, metrology-based closed-loop machining, integrating factory-wide systems with machine-to-machine and human-to-machine interfaces. Before we go ahead and dive into his presentation, I want to remind everyone in the audience that there will be time for a Q&A session at the end. So you can submit your questions at any point during the presentation. There's a Q&A icon that you'll see in your control panel, and you can type directly in there. We'll get to as many questions as possible. With that, I'd like to go ahead and turn things over to start the discussion. Ray, the floor is all yours.
Thank you very much, Michelle. Thanks for the introduction. Hello, everyone. Thanks for joining us in this webinar. I know for some of you, it's the lunchtime. Hopefully you had your lunch and joining us after lunch. If not, I think again, and just be patient for the lunch. So we're gonna start our meeting. I'm gonna be doing this meeting by flipping with the video and a presentation I have. I'm right now in front of a machine tool, as you can see, and this machine tool is actually ready for us to run some test programs as well. If we decide that we're gonna leave, that if anybody wants to see anything that we can do on the machine tool, we'll leave it at the end of the session and maybe at the Q&A, okay? So with that, I'm gonna go back and share my screen again, my presentation. So again, my name is Ray Karadayi. I started AAT back in 1987. So we have started AAT really as a software company specializing in metrology software. And we started as the first, one of the first, I should say, CAD or graphic-based CMM software, and that was in the late 80s. Our company name is Applied Automation, and my background actually is in automation. So our hearts is in applying metrology into automation and automated manufacturing, machining, and which leads us to our topic today, which is the smart machining with metrology. So we like collecting data. We don't like just reporting that data for somebody to look at and decide, but how do we use this data in an automated way by introducing it as an intelligence feedback to the machining process. So that will be our topic today. We're gonna be spending our time with that. Just to give you an idea of where we are right now in our Michigan office, which is our headquarters. You're looking at, I'm way back in this image in front of this machine, which is the DMG-Mori 5-axis table machine. This is where I am. In this location, we have a number of different machining centers, you know, CMMs, all the state-of-the-art technology in terms of sensors, laser sensors, you know, analog sensors. So we keep this office, this lab, ready for us to do development, innovation, and open to our customer base to get training and a lot of testing that we do for different types of projects. Okay. So again, just brief our agenda. You know, I'm gonna introduce, you know, our presentation, our webinar, talking about metrology. Why is metrology important in manufacturing? because we're going to be doing this metrology, gathering or measurement directly on a machining center, then we need to speak a little bit about the machine tool geometry. How can we trust the data that we're going to get from the machining center, and what are the issues that we could be facing, and how we can eliminate those concerns. Since we're going to be using different sensors to do this, so we're going to spend a few minutes discussing what kind of sensors available to gather this kind of, these metrology information on these machines. And then we're going to get into our heart of our topic, which is how do we then use metrology to make this machining process smart? So we're going to have a number of different examples of it, how, talk about the process of it, and how do we not only make the machine tool smart with that, but how do we make it adaptive, in terms of using the machine metrology data into different types of machining processes. And I'm going to have a number of different application examples. Hopefully I'll be showing us some videos of those, but at the end we're going to discuss, maybe there will be questions, I'm hoping, and we can then discuss different specific applications as well. So with that, let me go to my next slide. So first, I want a kind of overview of this kind of process. Normally on any machining process, we have a setup, then we machine it, and then we're done with this part. Maybe somebody else checks it. But in this case, just like creating a CAM program, we will be creating an offline measurement program. So we're going to be talking about that. So then, the program will be ready on the controller. Then we're going to talk about how do we make it work with a probe. So how do we trust the probe data? We're not going to look at this application just to use the machine tool like a CMM, but we're going to hopefully collect this data, measurement data, in relation to everything else that's going on in the machine tool. So we're not going to just look at a machine feature size or some part location or feature location, but we're going to look at this data in relation to what caused this and how do we then correct it, right? So for that probe calibration will be very important, not just to any cutting tool like a milling head or drilling tool, but even water jet cutting or maybe some laser cutting that is kind of a focal point in that case, not a point that we can touch and feel, but something that we can relate by doing an advanced calibration. So while doing it, we want to, like I said earlier, we want to trust the data that we're going to collect. So how do we then incorporate some tools with the machine tool geometry verification? Then we'll do part setup. We're not talking about just simple locating of a feature or something, but we're going to talk about how can we calculate a best fit alignment that is compared to a CAD model, and then how do we then send it back to the system as a warp offset. So with that, we will lead into machining. We'll do some initial cutting. We'll then measure. So we're now getting into the in-process part of this metrology application. We're going to measure the part directly on the machine, see what's going wrong with it, to make determinations first by looking at the metrology results, but then correlating those results into machine tool parameters that can compensate for it. And then doing those feedbacks, doing our finish cutting, and then we'll be able to do a final inspection of the part. So this is kind of the logic that we do, and not all of them would be applied in every case, but in general, these are the type of things that we will be doing. Now let's talk about, again, we keep referring to machine tool, metrology on the machine tool, but let's talk about what is really our main goal in machining, right? Our main goal would be making a part. I want the part to be dimensionally correct. So we really, all the machine tools right now are designed, mostly from a CAD model or some nominal specification, so that we create the cutting tool path. And we're hoping that by the time the part is finished, we're gonna get a part that is meeting our specifications, right? So that's our goal. If we were achieving that, we would be very happy. We don't need to do any measurement on the machine. We don't need to rely on external, devices to do it. So that's our goal. But how do we get that? How can we achieve that? So we know that there are a lot of issues while doing this process. There could be, for example, a part setup problem, or we have to invest very expensive holding fixtures to know that the part is in the right location, or we may have to spend a lot of time to make sure the part is in the right location to just even start the cutting process, right? So, but as we're cutting it, we may be having other issues. Maybe our tool is bending, depending on the part geometry, or maybe there's a tool wear, or maybe there are thermal expansion issues. So all of those, right? So now, one way to eliminate all of these, or at least be aware of what's going on, is by applying this measurement directly on the machine. So that's what we're going to be doing. So in other words, what we call digitalizing metrology. Digitalizing metrology is really collecting the data where the parts are being made, but being able to rely on this data, the quality of the data we're gathering, so that we can then make decisions on how to apply to a machine tool parameter, or maybe in some cases share it with other machining centers that are working on the same part, maybe in different operations of the part. Okay. So then let's get a little bit closer to this metrology data. What is metrology? So we all know that, when we're measuring a part, we get some dimensions from it. On any machine tool, we have all these. We may have already some measurement capability, finding a Z location or a size of a hole or something like that. But with real metrology is a lot more advanced than that, right? So we may be dealing with a true position call out that's based on a number of different complex datum structures. We may be looking just not the part size, but the part's form or the shape, especially nowadays, with the parts that we're making on these machine tools are not just making a simple hole or something. Maybe it's producing a turbine blade, or maybe it's producing a gear profile, or some kind of a medical part that has a very complex shape. So the design is really in the CAD data. Then we have to then relate our measurements to a specification that the designer put and collect that. So it's a lot more than just getting some XYZ data or some diameter, size data. Okay. Now, traditionally, how are those data gathered? So, a lot of manufacturing companies will have a coordinate measuring machine that's external, away from the part, or maybe they will have some shop floor measurement device if it is a production environment, But all of these devices, although they can do wonderful jobs for what they're doing, the problem is every time we have to remove the part from the machine, we have to take it to this device and collect this data, right? So that's the main issue. So, but when you do that, as soon as you remove the part, then you're left to do two things. You will find that the part is good. Hopefully that's our goal. The part is good, then we don't need to worry about anything. Or we'll see some problems, then understand and examine what are the causes of these problems and how do we avoid it on the machine tool. So we have to do some feedback to the machine tool or some adjustments to the machine tool, right? So now there are also macros on the machine tool. So if I want to do machine, if you look at a lot of the machine tools already have a probe, and they will have some certain macros that runs, but those macros are really designed for really specific simple tasks. Or for example, finding a Z height of the part, location of the part, maybe a location of a feature. Or we see a lot of companies have a couple different engineers keep managing a lot of different programs that they have that does more complex things, maybe calculating some kind of a formula on a profile and applying it directly. But it makes it very difficult. It's very difficult to manage this. All the calculations are done in the controller level, especially if I need a method of comparing to a CAD model. It's impossible because, it's impossible to bring a CAD model directly on the CAD on a G code level measurement and use. So then what is our solution? Our solution then is, okay, let me try to go, okay, here. Our solution then is integrating a CMM software directly into the machining center, right? So how does that happen? How can we do that? So I have a couple images here, but I'm going to also show it on my machine back here. You know, we're going to have a CMM software, which is, in our case, we call it CAPS. CAPS is computer-aided part programming system, and we have it as a CMM software as CAPS TMS. But in this case, we have an NC version of it. We call it CAPS NC. So this CMM software can be on a laptop or a PC directly next to the PC, machine tool, connected with a direct interface cable, which means that now we have a bidirectional interface between the machine tool controller and the software. And obviously the machine tool controller really commanding all this. So in other words, just because we have the CMM software here does not mean we need an operator that's an expert of this software. This software will live directly as a black box part of the whole system by having this bidirectional communication. So there's a short video here that I'm going to run. So the whole thing that the operator has to do is go there, hit the cycle start, and run it in the G-code level, and the software will then, the controller will talk to the software, immediately start executing this program, which you can see on the little image that we have on of the software. So the whole idea is integrating the CMM level software really seamlessly with the controller so that it can have bidirectional interface, but also easy to operate, because we do not want operators to become a CMM operator either, okay? So how is this done? A little bit, let's take a closer look at this process, okay? So while I'm explaining this, I'm gonna run another video here so that you can see this on another machine, which happens to be the machine back here. So the operator goes there, picks the program, starts it and walks away from it. And immediately the program that he picked on the controller invokes the software, makes it open the program that he's running, and becomes a part of the machine really. So in other words, the program is on our NC software, CAPS NC laptop, but it's linked with the controller. So we have live interface with the controller. But a version of this program is already posted, and it's in the controller itself as G-code. So this G-code is no different than any other cutting programs, really, because that way, the interaction between the cutting programs and our measurement programs are very, very easy to do, okay? So he runs this program once it's posted there, and we have live interfaces, live feedback, and you can see it in this video, as the machine tool is moving to measure this engine block, we actually have a real-time feedback in our graphics environment. You know, we may not even care to see it. Some users even hide the screen, but you know, it's there for us to see. It's there for us to immediately see the results that we're getting. So in other words, we don't have to wait for the whole program to finish just to see the results of the first point or the first feature that we measure. But more importantly, as we're doing this, as we're calculating this, we may be doing feedback to the controller, right? So we may be, for example, actually in this program, the first thing it does is it measures a surface and a couple of the bores and creates an alignment, a coordinate system for it. And that coordinate system is then transferred into the controller. Now it becomes a work offset. So that work offset is now something my cutting programs can immediately use, but also my rest of my measurement program can also use. So with that, we can then collect the rest of the data. We're not limited to how many points we can take on these features. We can take a number of points, or even use maybe a scanning probe and collect a lot of data. And then we can generate very detailed metrology reports. So this is a closer loop of what's going on when the software is running on the machining center. So now let's go to the next slide. Okay, so now how do we implement this? Okay, so just a little bit wider view of things happening. Obviously, again, the primary goal of the machine machine tool is to make parts. Our metrology implementation here is only aiding that so that it can be done accurately at minimum cost and quickly. Although we may be adding some measurements to it, the overall time spent is faster. But to program that, we do that in the engineering office. We don't have to use the machine tool to do this. We will have a virtual machine environment in our offline software. We're going to be able to simulate all the motion of the machine, and we'll be able to create really a CMM software, CMM program that does all the datuming, all the reporting, all the future constructions, true positions, perpendiculars, all of these, right? But then we may also decide, okay, I'm doing this to create a metrology report, which I can do, but maybe I'm also doing this to create a feedback to the controller. For example, if I'm measuring some blade, let's say, or some, surface part, I can then create a work offset by comparing the data and feedback to the machine. So I can program that kind of stuff. I can program a coordinate system calculation, and then I can also decide which work offset does it need to go into the controller. So I can do that. I can also apply maybe in the in-process part of it as some kind of decision-making in terms of a tool compensation, or maybe some logical feedback that the CAM program can decide in terms of where I find my stock if I'm cutting a part, from a blank, where is my stock, so I can decide, maybe the CAM program will decide to do some decision on that, So that could be as well. So we are programming all of these here, not just the metrology part of it, but all the machining, metrology related machining part of it as well. So then we will be bringing it to the machine tool, and then it will be running as in the previous chart that I showed, as a closed loop system. Okay. So now let's go to our next slide. So we mentioned offline. So let's spend a little bit more time on this. Offline really works as a true virtual environment. So it has a very intuitive user interface. You can actually manually rotate the table, positions, simulate different work offsets. Where should my part be? Where is my volume limitations? Even what kind of probe do I need? I can build, I have the whole catalog of all the probes available out there for purchase. I can graphically build them and then create this program. And then when I'm done with that, gonna go to the next slide, I can simulate this program. So this is an example of a simulation in the offline area. So I have also a feed control that kind of simulates how the feed rate should be in the graphical execution. So this is now simulating a table rotation, picking the datum, futures. Then it's gonna go pick some surface data, because on a part like this, we're gonna need, maybe this part came from casting and we're gonna be machining. So we can now find out exactly where the surfaces are and do a best fit of this data to a CAD model, which would be impossible in any other way. It would take a lot of time to do this. So this would be automatically doing it, but we are now simulating the process here. And then at the end, it will calculate all the coordinate systems. That way we can feed it back to the machine tool for cutting, okay? So we talked about it. So I think I understand why we're doing it, but can we trust this machine tool? What happens? The machine tool is, after all, not a CMM. CMMs are calibrated and they're not large forces, or they're under controlled environments, right? So to do that, we can do some geometrical verification of the CMM. We have really, again, two goals here, two primary goals of doing this. One is, again, aside from all the measurements that we want to do, number one, we want to know that our machine tool geometry is good for cutting. I don't want to find out that my machine tool had some problem with the table orientation or the head orientation for whatever the reason, after I made some expensive part and they measured it on the quality control machine and told me it was wrong. I don't want to do that. I want to know that my machine tool, in the volume at least, that I'm going to do this part, I can trust. So that's number one. Number two, I'm going to be creating metrology data, And I want that data to be traceable data. I want to know that I can trust this data. I can create, reports from it, metrology reports from it. And so that's the other reason. So, but that can be done, it turns out, depending on the machine tool configuration, depending on what we're trying to achieve, in very, very simple and inexpensive ways. So on the screen right now, we're looking at a gauge block, what we call a tetra ball bar gauge. I happen to have one of them here. You can see it here. So it's very easy. It comes with different sizes. We place it on the machine. By measuring these 4 spheres, we can have a pretty good idea of the machine tool geometry in that volume at least, right? And there are, of course, other ways. There are very expensive ways of connecting all kinds of scanning, laser collection, measurement data that in real time calibrates the machine. That's also available, but it's very inexpensive, not very easy to use, in my opinion. But something like this can be very, very quickly done. Or on a machine tool that has a table, by just measuring a sphere and tracking it, we can see if the machine tool is having an issue with the table center or the head center orientation. So in this image, we see that. So I may be checking very quickly the table center and see if it changed it. Can I trust it? Can I feed it back? So I can also measure that and update the controller in real time. So this is not just for me to have good measurement, as I said earlier, but it's also for me to know that I'm making good parts. So I want the CAM part of it or the NC program part of it to benefit from that as well, right? And same thing for the head machines, or same thing for the general geometrical characteristics of the machine, like linear errors, maybe squareness errors. I can see, I can trust it, or if I don't trust it, can I then correct it? Or in the worst case, I can gather historical data and maybe schedule a maintenance, so that I'm not stuck realizing the machine tool is not functional, but I can predict when it's going to be out of tolerance, so that I can schedule it maybe in a night shift or something, so that they can come and check what's going wrong. So we can do that kind of stuff. Okay. We have users using this technology, and some of them apply this in their part machining process, right? So what they do is, what can be done is you put your gauge, and it can be this gauge or it could be some other gauge, doesn't matter. You check this, you gather data, you know that your machine tool geometry is good. You do your setup, you do your machining, you can then create your measurement reports. These are all automated processes, by the way. And at the end, you can go back and check it again, check the same gauge again. So if between those two, all these processes, those two results agree, there's no problem, then you say that you're very confidently can say that your part is good. In terms of the geometrical characteristics of the machine, you don't have a problem. So this is one way of a process that the customers use it in real life right now. So now next I want to go into sensors briefly. So there are a number of different sensors that are available. It turns out actually a lot of the machine tools already have a probe, because they need to do some simple setups, and in most cases, these probes are what we call a kinematic probe, meaning you really cannot measure a point in any random direction because of the kinematic mechanical structure that is put on the sensor itself. But in our software, we have a way of calibrating that. We have a way of what's called the lobing errors. We have a way of automatically calculating that and correcting that. And unless the part shape doesn't change very rapidly, that produces very, very good results, even when you're measuring along the vector. But of course, for high precision applications, we recommend strain gauges. Now, strain gauge probes. Now, analog probes are coming along, so there are going to be a lot of that we're going to see. But in this company, one of the innovations that we've done very successfully is the non-contact lasers, sensors. So we can integrate a blue light laser into the spindle or the side of the machine on a 5-axis table machine. And instead of looking at point data 1 point at a time, we can create a point cloud data and look at the whole part and do some analysis and some decision making on a point cloud. So there are applications that works best with this kind of sensor. Okay. So now, when we put these sensors, including our laser or touch probes, as I said earlier, we're going to calibrate it, not just to produce data for measurement, but we're going to calibrate it so that we can provide feedback to the machine. So all our calibrations, it's going to automatically find the runouts of it, electronic radius and all that, but it's going to create these in relation to the cutting tool that we use. So that if I can't find some microns or thousandths error on my part, I can confidently tell the controller to go back and take that, and he'll be able to go use any cutting tool that's available and go and finish that surface precisely. So another thing that we do is we can use multiple styli so that, in some cases that's necessary, and we can go not just touchable by the main probe, but on another configuration that we can touch on the side, we can do also those. And lastly, we're getting into a lot of applications, more and more applications that we can use multiple probes. So we can use actually a touch probe and a laser or multiple touch probes at different configurations. And the same program, measurement program, can switch from one to the other and complete the whole measurement program with that. Okay, so just a little bit more information about the laser. We calibrate how the laser integrates with the machine, what we call a latency error, so we calculate all of those. We use the laser by sampling at very, very high frequencies so that we can get a very dense point cloud and get all the details. And we use this for not just creating a point cloud and letting somebody look at it, obviously, but we can extract geometrical features from it to, very small circles that we can extract all the tooling ball data, surface data, and point data. So instead of bringing, let's say, a laser tracker machine on a very large part and measuring all these points one at a time, we can very quickly be scanning the surface and then calculating all this data directly from the point cloud. And another thing that we do is, since we kind of reverse engineer this part by getting this point cloud, now we know exact shape and orientation of the part. Then we can apply, later on we're gonna talk about this more, but what we call an NC fitting. In other words, I can take my cutting program and adapt to the shape that I have. So if those of you know how a post is made, they make it from a CAD model, which is a perfect part, but if the part is not perfect or not in the shape, then what we're doing is we're applying this post on the actual part rather than the nominal part, so that we can do our cutting process quickly. Okay, so now we discussed our primary goal, obviously, is to make good part, but we do this by breaking into different pieces, in the whole process. We do a part setup, we do it in process, feedback, measurement and feedback, and then finally we create quality reports. So I know that I don't want to run out of time, so I'm going to go a little bit faster here, skip to here. So in the closed loop metrology then, what are our feedbacks? Where are our feedback areas, right? So if I'm setting up the part, I can set up the part, create a relationship of the part. I'm not going to even talk about simple cases, but I'm going to talk about more advanced case of, let's say, that impeller that we saw earlier, comparing it to its CAD model. All right, so I can compare it to a CAD model, calculate the best fit, and write into the controller so that it can go there and finish this part. But while it's doing it now, maybe I'm facing some other issues, such as maybe tool wear. If I'm finishing a big die, let's say, I may be having a different tool size from one side of the die to the other. We see all these kind of things happening. So then I can calculate that. Or I may be working with a part that's kind of a little bit a non-rigid part, let's say a thin airfoil blade or something, so that there's a spring back effect. So then I can look at what we call a dynamic tool compensation, not the tool shape as you see it maybe with a laser measurement device that you may have on the machine, but how the tool behaves in the actual cutting process. So we do all these, and then we produce our part with the 100% quality report. Okay. So we can talk about more about the work offsets. There are different examples of it, but we want to emphasize that the fact that we can do this with a CAD model in the real operation, is very, very important, I think, and very powerful. Okay, and that is fed back to the controller in a number of ways that is most suitable to your machine type and your application. In other words, if I have a 5-axis table, maybe I want to make sure that I put my part and I want to drill my holes through the perpendicular to the surface. Maybe I need to apply this offset as a table correction, so we can do that as well. And then in a lot of cases, you may be dealing with multiple datum setups, and then you start with a fixture, but then you get into the part because your final alignment or work offset you will create for cutting has to be from the part. Then you can apply what we call an iterative part alignment. So we can start with a simple datum on a tooling ball or something, get some of the data on the fixture, some of them from the part, and then going to the next level of the alignment, then go iterate, finding all these target points that are designated for us on the surface. Some of them are on the big surface, but some of them are on the leading edge, right, in a very tight area, So we get those, then we create this alignment and report this alignment, verifying that the part is now located perfectly. Now we can start our cutting process. Okay. And lastly, what we call NC fit. So what if my part is not the shape that I think it is? Maybe it's behaving non-rigidly, maybe there's a flexing, maybe because of the process it came, which happens in like sheet metals or composite parts, maybe there's some twisting and turning if I'm gonna be doing some drilling and trimming operation. Then I can go measure my data and then apply this as a try and NC fit to my cutting program, so that my cutting program cuts the part where the part is, now not where it thinks it is, right? So, and another side of that is, if my machine tool does not have an ability to align the head to the actual part location for the 6-degree of rotation, then this software, this option can also align the head always so that it's always cutting in the orientation that is expected by the CAM software. Now let's go into a little bit different application, again, in the ink process, right? So we have a feature in the software where we can create a process of starting the cutting program directly from our measurement program. We can start the cutting program, let it do this cutting, and then check the features that we're cutting, and then make the decision that this feature is finished properly with the tolerances. So all the decision making is done in this software in this case. So we call this, we can, in two different ways. It can be a cut, measure, cut cycle. In this case, we start with a rough cut. So the program that we create from the software initiates the rough cut. So the first thing that you see is it starts the cutting. And then we measure the size, and then maybe, determine if we need to apply any dynamic tool offset, as I mentioned earlier, or some correction. And then, let it do the finish cut, and then loop here. So there may be some iteration here until we bring the feature right in the tolerance zone that we want. We don't need to cut the part to the specified tolerance, but we have a tolerance band. So we can decide, I want to get into the tolerance, and I'm happy with this. I don't need to waste more machine time, let's say, okay? So that kind of decision can be done here. Or it could be just a measure cycle, where we just locate the part and then let it do a finish cut, and then we check it and then we cycle it, okay? Now, if you look at this image, we have a pattern of this kind of features here. So this this kind of application can also then loop on all these features. It will make sure that one feature is finished, and then it will then make it go to the next area without having to make a long cutting program either. You would make the cutting program only for one of them, then we will be translating that, transforming that into different areas. Okay? So that's one way of doing this. And this is where the software decides that the cutting process is done and it initiates the cutting process. Now, the opposite of this can be also true. So maybe you have a CAM system, you create your cutting program, and you would like to call the measurement program that we did for this. So in that case, you would start the cutting program, and really logically it's the same thing, but implementation is a little bit different. So it would be starting the cut, and it would be running one or two, a number of different cutting programs. Maybe it will, measuring programs. Maybe we'll start with doing a part setup again. We'll do that, we'll write a work offset, then we'll do cutting, and then we'll measure, let's say on this blade, maybe what I'm interested in is I'm not really sure what the stock that I need to start with. I don't want to run a very long program that does a lot of air cutting and then eventually gets there, or the opposite of is risk cutting, going too deep and breaking the part or hurting the machine. So what we can do then is, in this kind of application, we can find out, we can measure this blade, find out what the stock is, write that as the value into the designated address in the controller, and the CAM software can then decide what needs to do. Maybe, for example, it will decide, well, based on this stock that I see, I'm going to run this program as opposed to this other one that works with another stock value. So that would be an example of it. Okay. So finally, when it's all done, we're going to get inspection reports. We have a number of different ways of creating measurement reports, both graphically and in Excel files and all that. So, and a lot of times, again, these reports are generated because this is on the shop floor. This doesn't have to go back to another system so that an engineer analyzes it, unless they want to do it. Normally, it will be run here. PDF files or Excel files will be saved on the server. In fact, if the software sees a condition that is not acceptable, it can also generate an alarm or even send an email or a text message to the engineer responsible so that he gets, it gets his attention. Okay. Now, we can't ignore the human factor. If you go back and realize how things were done, so normally we have a huge influence of the human factor, right? So, for example, if I measure a size and I apply that into a tool offset or some work offset value, maybe I got some value from a hard gauge or something, then the operators enter it, and the big problem there is that it slows the system down, right? It's not an automated system then, I know that there are other ways to interact with the gauges or external, but those are not very common. So a lot of times the operator will be doing it. So using this kind of smart metrology on this machining application, we are kind of eliminating or minimizing the operator human influence and avoiding all the errors that can come along with that. Now, another bigger view of all this, so all the things that we discussed is at one machine level, but we can also look at the factory level. So we have other software that we can collect metrology data, not only from the machining centers, but all the measurement devices that's available in the system too. So we will be collecting them in this, different databases that we can create, and then we can look at the charts, the bar charts and whatnot. So that would be a good visual to see how our factory is doing in this case. So we're really creating a factory view of all the metrology data they are being gathered from all the machines, right? But more importantly, because now that we have this data here, we can then create some decision making here as well. We can look at the data, maybe history of the data, apply some kind of a formula, and then say, okay, this machine that measured this feature was made by this machine here. Now I can update the tool offset directly to that. So even though it's not measured on that same machine, even though it's done externally, I can then link all the machines together, kind of create one big machine that works all in agreement, all by transferring this metrology data. Okay. So this is something very exciting personally for me. I think we're going to see more and more applications with this kind of software in the future. Okay. Now I'm going into some examples. I'm not sure how we're doing by time, but I have a few more minutes. So I want to show you some examples, some application examples. So in this case, we're looking at a mill turn machine. So we're not only producing a part in total automated way, but also integrated a robot that can load and unload parts by itself, right? So it would load the part with a blank like this. Then our software, it goes on the main spindle here. So our software would do a setup, find out exactly where the center is, where the Z location, the surface is, because those blanks may not be exactly the same size, and we don't want them to be maybe more expensive to do that, So we will adjust it with the software. So we'll do very quick measurements, and then we'll let the software run, create all the features based on the specifications and where we want it to finish into tolerance limits that they have. So we don't really force it to go always to the zero tolerance unless we want to. So we can just bring it into the comfort zone within the tolerance, decide it's done. And then there will be iterations here. There will be finishing and a measurement iteration very quickly, and of course, automatically. And then when it's done, it will be generating the report, but automatically sending that part to the sub spindle, repeating it there, finishing it, and then the robot takes the part and then puts the next one, and the cycle then continues. So, however many parts that they can locate in their part holder, then the robot, they will start the cycle. It may take a day or whatever, depending on the part, but all the parts that we will be measured or created within the specifications, and there will be a metrology report, quality report generated for each one of them and saved on the server. Okay. Now, I believe this is a video that I want to run here quickly. This is showing us, let's find the sound. So this is an example of using laser on a sheet metal scanning, and you can see how fast we're able to scan it. So we're running the scanner in real time, collecting that data, and the point cloud will pop up, and then it will start extracting, I believe, 2.5 millimeter holes from this sheet metal. So it's rendering the data, and it will be then extracting. See, now we see that very quickly it's gathering, extracting these features, which after that we can do more alignment, let's say a best fit type of analysis, or just generate the report. Okay. So that's the first video. I have a couple of different videos here. This video is one of our machines here, also with the laser. In this case, we're measuring an artifact. So just to show you how, so this is a real, it's not a very good video, but it shows you the whole video, whole machine. That's why I picked this. It shows you as the machine tool is moving here, collecting data in real time. We are seeing the laser, and then we are going to go collect the data in our CAD environment and do all the analysis that the point cloud software can do in terms of comparing it to a CAD model, extracting features. Okay. So we got a couple more videos before we go to our Q&A. This is an example of a blisk or a, I showed this earlier on another picture, blade measurement. So in this case, again, the operator decides not only the cutting program, but which blade it should run. So we would have only one measurement program along with one cutting program, and it will then go to the blade that he wants to run, and it will run that. Okay. So I'm going a little faster because I want to leave some time for Q&A. This is a aerospace part on another 5-axis DMG-Mori machine. So again, in this case, the part is finished, we're just creating a quality report. Okay. So although we're doing it in very detailed measurement, we're really running these programs very, very fast. It really does not add a lot of time into the production cycle, but we're getting not only the report that we want to see, but maybe some more useful information about how we can make this part better. Okay. This is an interesting application for a precision turning application. In this case, our goal is to create a shape in a turning application. This is just a sample part. But what we are cutting program, which is done from a CAD model, working on it, but maybe we have a lot of different problems here. We may have a tool problem, spring back problem, maybe temperature problem. We're putting all of these errors into the same box, looking at the actual profile, and then in real time creating a correction table and writing it back to the controller so that it can then go back and finish the part automatically. Again, everything that we're doing is automatic. So in other words, if I have not done it that way, I may be getting this shape, exaggerated obviously, but then after cutting, after applying this, I'm going to get a very, very good profile on this part. And this again is real application that some of our users really depend on in manufacturing their parts. Okay. Now on my last slide, I just want to touch base on my conclusions. So we have again, this process, all of this process helps us create parts that we can confidently say it's within the tolerances or expected specifications that we want, right? So that's our goal, and we do that at the minimum cost and minimum time and automatically. But doing that, really, we're doing it by applying techniques on the pre-process part setups, and I've gone through a number of different ways for that. In process, same thing, looking at the tool compensations, maybe terminal errors, things like that. And automation goals, maybe we're creating some decision making back into the controller, which the CAM program can decide, but also make the data available throughout the factory so that other systems maybe can use that for their benefit. And then finally, inspection reports. Okay, so we reduce at least the dependency of our processes on external measurement devices. We can confidently measure it, get our measurement results here, and get data on all the parts that we're making. I think this was the last. And I want to thank for paying attention to my webinar. If there are questions, I'll be able to answer now.
All right, Ray, thank you so much for providing those insights and exploring the benefits and process of smart machining with metrology feedback. That was very informative. We will now go ahead and open it up for audience Q&A. So if you haven't done so already, you can submit those questions by typing them into the Q&A icon you'll see on your control panel. And we did receive a few questions already, so I want to go ahead and start with those. The first question we have here, do you communicate with the machine CNC directly in order to synchronize the machine movement with the remote offline measurement simulation? And if so, what type of CNC do you support?
Okay, thank you for the question. As I mentioned, there are two versions of this software, or two configurations. One is offline. Offline does not need to connect with the machine tool. It has the virtual environment for the machine tool where we do all our programs. Online version of it, just the one that I see here. Is there one? Okay, here, yeah. So this software is directly connected with the machine tool. So we have an Ethernet cable, in this case with the Siemens controller, and we have a bidirectional communication protocol. We can communicate with the machine. So most importantly, as the machine tool is running, we get live updates of the status of the machine tool. Yeah, where is it? What's its feed rate even? And is there a point that it just took? And what is that point? And immediately we receive them. Immediately we update our software with that information. Now, in terms of what kind of controllers, practically all the controllers out there, popular controllers, you know, Siemens, Fanuc, Heidenhain, Okuma, Mazak, Fagor controllers, you know, I'm sure I'm missing some others. Haas machines, you know, we have interfaces for all of those.
Great, thank you. And then another audience question that came in, how do you ensure the in-machine measurement accuracy if the machine resolution is the same for cutting and measurement? For example, a CMM usually has 10 times higher resolution than a machine tool. And if the in-machine measurement is targeting at relative dimension measurement, like hole inner diameter, outer diameter, that's fine, but not for the dimension needed to be measured based on machine resolution. So do you have any comment on that?
That's a very good question as well. So if you look at the history of the machine tools, you know, a lot of the older machines have that problem, maybe lower scales, maybe not even a linear optical scales, you know. But a lot of the applications that we do with this technology are modern machines, like the one that I have here has very high, you know, resolution scale. In fact, some of them that we've seen maybe it's even better than CMM or as good as the CMM, right? So if we face an older machine, let's say, most likely those type of machines won't even have the strict interface capabilities, but still we can connect with non-direct methods. There are other ways. But in that case, what you have to think is what your tolerances are, what your acceptance criteria are. Obviously, you know, the question is very right, saying that we're not going to get better resolution than if you're measuring one point on the end of a part, better resolution than the machine can give me, but is it still within my tolerance specs or not? So if that's not the case, then we would not want to do an application like this on that type of machine anyways.
All right, thank you. And another question we have here, what does the machine tool operator have to know in order to operate the software?
That's a very good question as well. You know, we want to run the whole system automatic. So we, you know, as I mentioned, this is really a CMM software adapted to the machine tool. By saying that, what we really mean is that we don't require the operator of the machine tool to know anything about this software. In a lot of our applications, installations with the customers, they may not even have the screen there. It may be somewhere else, or it may be high up there just so that they can look at but not interact with it. So the operator of the machine tool doesn't need to know the software. All he has to know is if he is the one who needs to pick a program, obviously he needs to know what measurement program to run. Maybe a setup program or maybe some in-process program. But with inner luck, our really ultimate goal is not even needing any operator, because if we set up our CAM process automation, then the system itself is going to decide when a measurement program should be done and when it needs to switch back to the cutting program.
Great. And then lastly, could you talk a little bit about the return on investment for this technology?
Absolutely. This is a very good question as well, because in the early days when people look at this kind of solutions, they always question, you know, typical questions were, okay, the machine tool geometry or the resolution, the question, can you really do this type of measurement? But more importantly, why would I want to spend my time taking points, measurements on the machine tool? Really, our goal is really not to do that actually. Our goal is to minimize your downtime of the whole process to get your end goal, which is to make a precision part, right? So a lot of times, especially when we're talking about precision parts, you need to involve some kind of metrology anyway. So you need to either have somebody measure a size on the machine with a macro, maybe, or externally with a shop floor device or a CMM, and then get that data back here. So if I'm measuring let's say if I'm manufacturing a turbine blade, let's say, and I've seen customers telling me all the time, they may have like hundreds of machines, but they're really using them at 50% capacity only because they're waiting for the machine tool to get data from the CMM so that they know how to continue. So those are the applications that we're targeting for. Obviously, if you have a very robust application where it doesn't need to involve a lot of the measurement, you don't need to use this kind of solution. But if you're dealing with an application where metrology helps you, then overall time is saved drastically. In this part setup, it's saved. In the final tool corrections, it's saved. And in the quality of the part that you produce, and now you don't have to repair it, it's saved. Okay.
All right, thank you. Well, we are about out of time, so we're going to go ahead and wrap up the session. Ray, I want to extend a very special thank you to you for presenting those insights today. It was very informative for our audience. And I also want to thank everyone in the audience for joining us. We are happy to have you with us, and we look forward to seeing you in the upcoming IMTS conference sessions. Have a great rest of your day, everyone.
Thank you, Michelle, and thank you, everyone. Bye-bye.